Hello class, Professor Anderson here. Let's talk about Gauss's law in a little more detail. So how do we write Gauss's law mathematically? The way we write it is the following. Integral of E dot dA equals Q enclosed over epsilon naught. Now, this maybe is introducing some math that you haven't seen before, but let's talk you through it. Integral, we understand how to do an integral. What does this little closed circle mean? That means it is a closed surface. Okay, so you need a closed surface for this particular integral. That surface could be a sphere, it could be a cube, it could be a cylindrical surface, but it has to be a closed surface. E, of course, is the electric field, but it is the electric field at the surface of that closed surface. Okay? Dot product, we know what that is. Okay, and we know how to deal with that mathematically. dA is a surface area element for that particular closed surface. Okay, so we need to dot the electric field at the surface with the little surface area element, and then we have to integrate over the entire closed surface. What about the stuff on the right side? Q enclosed, that is our good old charge enclosed within that surface. So if it's a closed surface, it's everything inside of it. So for a sphere, it would be all the charges that are inside that volume of the sphere. If it's a cylinder, it would be inside the cylinder. What about epsilon naught? That is our good old permittivity of free space. Okay, so this is Gauss's law in mathematical form. What is the goal of applying Gauss's law? The goal is the following. We want to, one, exploit the symmetry of the charge distribution. And what that means is if it's a point charge, we want to use spherical symmetry. If it's a line charge, we want to use cylindrical symmetry. And if it's a planar charge, we want to use Cartesian symmetry. Okay? The second thing is, once we exploit that symmetry, we want to stick in the E field at the surface and dot it with the dA such that the dot product disappears. Now, what do we mean by that? What we mean is that E and dA have to be either parallel or perpendicular. If they are parallel, then E dotted with dA, remember dot product would become E dA cosine theta. Theta would be 0, and so that cosine term goes away, just becomes 1. Or if they are perpendicular to each other, then E dotted with dA, we'd get a cosine of 90 degrees, and that term would be 0. So either way, it's going to simplify our math. Okay? And then we use Gauss's law to calculate E. Now I want you to look at what I wrote there. I said we use Gauss's law to calculate E, but I didn't put a vector sign on top of it, okay? What we are calculating here is the magnitude of the E field. Gauss's law tells us the magnitude of the E field, but it doesn't tell us the direction of the E field. The direction of the E field has to come from the symmetry of the problem, back here in step 1. And when we do a couple examples, you see exactly what I mean by that, okay? So this is sort of the goal of Gauss's law. Use symmetry to simplify this equation such that you can calculate an E field in magnitude. All right, and let's see how that works.